All right, so my students would probably say that those technical difficulties are my fault because they tend to follow me around. But my name is Royce Floyd. I'm from the University of Oklahoma, and I'm going to talk about a preliminary study that a couple of my students did on internal curing of calcium sulfoaluminate cement concretes. So Stephen Tanksley is currently an engineer with Half Associates, did most of this work, and then a current student, Mushtaba Ahmadi, is working on extending this project to examine some new things. So I'll talk a little bit about what I mean by this cement, where internal curing comes into play, then go through the methodology of this specific work, the results, the conclusions, and then the work that we are currently doing. So as everybody in here knows, and as a lot of what's been talked about, there's a lot of CO2 emissions associated with cement and cement production. Depending on how you count it, it's 5 to 10% of our global CO2 emissions from people. And there are a lot of alternative materials that are being talked about in the concrete industry, one of those being calcium sulfoaluminate-based cements. And I'm not going to spend a lot of time talking about cement chemistry, but the basic idea is that they include a calcium sulfoaluminate material that reacts to create ettringite. It takes more water to make that reaction happen. And you can formulate the proportions of your cement with the calcium sulfoaluminate, calcium sulfate. A lot of them include B-lite or dicalcium silicate, and the mixture of those is going to give us different properties in the types of cements. So previous research has shown there are kind of 4 different types that you can think about. There's an accelerating additive that you add to the traditional Portland cement mix to speed up the time of set. There's a bolytic calcium sulfoaluminate cement, or a BCSA, that includes the B-lite mixed in with the CSA, and it's kind of a all-in-one cement. It also is a rapid setting material. Then you have an expansive cement additive and a shrinkage compensating cement. And we're really going to be talking about the type A, type B, and type K in this presentation. So most of what we have been dealing with at OU and in a lot of our research is the BCSA cements, which have a very fast set, between 30 minutes and 4 hours or so. And kind of where they come into play in this session, you get a lot of reduction in CO2 emissions, both from the reduction in energy that's needed to make this cement. It's easier to grind. You kiln it at a lower temperature. And whenever you actually are decarbonating the limestone, there's some less CO2 that is released there. So depending on how you count it, you can get a reduction in CO2 emissions 30 to 50% compared to Portland cement. And we talked a little bit about other types of CSA cements. There's limited use throughout the U.S. and Europe. There's limited production, which is part of that. But there's been a lot of work that's been done using the rapid setting cements for pavement repairs, some for bridge decks. Some type K or shrinkage compensating cements have also been used for bridge decks, but used a lot for concrete floors and tanks, where we need to limit or prevent cracking. There's been a lot more use of these materials in China. There's some great potential for precast, which is what a lot of work that I do is related to, but there's still a lot that we need to know. And there are a lot of questions that you'll see on these cements across the board. But there have been some good applications that are out there that have been there for many years, including a lot of highway pavement repairs in California. There have been some airfield pavement repairs done quite often. SeaTac in Rockford, Illinois are some good examples that are in service and performing well. And there have been a few structural repairs done using these materials. You'll see patches and things like that a lot, but in terms of structural concrete, this bridge connection repair in California is a good example. So when we think about these CSA cements and CSA cement concrete, we can get a rapid strength gain, so we can turn things around very fast, which is nice for those pavement repairs where we want to get traffic back into place. Potentially it's good for precast elements, things like that. We get that reduction in CO2 emissions from the cement itself. But because we have a higher water requirement for the cements, we can use a higher water cement ratio to be able to increase workability and still get the same strength and not lose anything on that end. And then we're able to get dimensional stability or shrinkage compensation, depending on which type we're using. So the BCSA cements have low shrinkage. The type K and expansive cement concretes actually expand and compensate for the shrinkage. But there's still, disadvantages that need to be considered, like the cost. Fast set can be hard to deal with. Contractors' experience with the material can be hard to deal with. But again, there's also just a lot of information we still need to know about these materials. And then kind of where we're getting at in this presentation is to get whatever performance that we want, whether that is the shrinkage compensation, the expansion, the rapid set, and good performance over time. So to react that B-light later in its life, we need good curing. And we have to cure for several days to get the full performance of this material. And so internal curing can be a good option for helping with that process. So most people here are going to know what we mean when we say internal curing. But internal curing is going to be additional water that's not part of the mixing water, typically from pre-soaked lightweight aggregate. That's what we're using in this case. And it's been shown to be able to reduce some shrinkage and also be good for low permeability concretes. So the objectives of kind of this preliminary study that we did was to look at the impact of internal curing on CSA cement concretes in comparison to a similar Portland cement concrete relative to compressive strength, permeability, length change, or shrinkage, depending on how we look at it. And so we looked at a rapid setting BCSA cement. We looked at a rapid setting CSA cement additive, so added to traditional Portland cement, a type K shrinkage compensating cement, and then a regular Portland cement. So we can, look at the mix designs here. If you really want to look at that closely, we can talk. But it's basically a 7-sack mix across the board, except with the type K shrinkage compensating being a little different because it includes 15% of that type K shrinkage compensating cement. We had a water cement ratio about 0.48 to 0.5. And then we only needed high range water reducer for the rapid setting CSA cement additive. For the lightweight concrete, we used an expanded shell lightweight fine aggregate. We looked at the absorption that the soaking time we wanted to use for this project. We evaluated a few. We went with 48 hours pre-soaking, which gave us an absorption of about 11%. And we try to follow the same procedure every time of soaking the aggregate for 48 hours and then draining it over a geosynthetic for about 15 minutes. So to give you an example, we looked at adding 5 pounds, 7 pounds, and 10 pounds of internal curing water per 100 pounds of cement for each type of cement. And so to do that, we adjusted the mix design by adding the lightweight aggregate and reducing the normal weight sand. And this is just an example of one of those adjustments. So our testing methods were to test compressive strength using 4x8 cylinders. Our typical times were 24 hours, 7 days, 28 days, and 90 days. But for those rapid setting cements, we needed to understand what was going on earlier. So we would also do tests at 2 hours and 6 hours for those mixes. We looked at the ASTM C1202 rapid chloride ion permeability as a comparative measure for that property instead of doing a longer term test. And then for length change, we did unrestrained ASTM C157 specimens for the rapid setting cements. Again, we started at 2 hours, measured at 4 hours, and then everything else started at 24 hours and went every day for the first week and weekly after that. We also examined for the type K shrinkage compensating cements that we expected some expansion. We did a 6x12 cylinder with a vibrating wire strain gauge that was included in the cylinder. So if we look at some of the results that we saw from these materials, if we look at compressive strength, we can see the blue bar being our reference mix design with no internal curing water. And I should say that all of these specimens were cured in air, so there was no external curing added to them. We can see that we consistently get a higher compressive strength with the 5 pounds of internal curing water, but we don't see a whole lot of difference with the other additions. And note that this is the CSA cement additive. If we look at the BCSA cement, so the CSA rapid setting material that also includes B-Lite, we see as we get to later ages some additional increase in compressive strength that's likely from the hydration of that B-Lite within the cement system. And then for the type K cement concrete or the expansive cement concrete, we do see an increase in compressive strength again at those later ages when we had 5 pounds and 7 pounds of internal curing water, but not so much at the 10-pound addition. And then if we compare with the Portland cement, we again see some slight increases as we added the internal curing water across the board. In terms of the rapid chloride ion permeability, we didn't see a whole lot of consistent results from these tests, but in most cases, as we can see here with the CSA cement concrete at the 28-day range, we did see a decrease in our coulombs passed. We didn't really see a definitive trend when we looked out at 90 days. For the BCSA cement concrete, we saw a reduction as we increased the internal curing water, but again, not a drastic reduction out at 90 days. For the type K cement, we did see, again, a slight reduction in the amount of coulombs passed as we added the internal curing water for each amount, all the way out to 10 pounds of internal curing water. And then for the Portland cement concrete, we didn't see much of a change for adding internal curing relative to the rapid chloride ion permeability. If we looked at the ASTM C157 length change, if we start with the rapid setting cement CSA additive, we can see the blue line there is our reference mix. There were some issues at the beginning of that test, which means that our reference may not be the best. But we can see as we go out to 90 to 110, 120 days that blue line ends up at the bottom, which means that we had the largest shrinkage when we included no internal curing water. And as we made those additions of 5 pounds as the orange line, 10 pounds as the yellow line, and 7 pounds as the gray line, we did see a reduction in that shrinkage over time. For the BCSA cement or the Bolitic rapid setting cement, we didn't see a definitive trend there as well, but we did see that we got a little bit of improvement as we added 7 pounds of internal curing water and actually saw more shrinkage with the 5 and 10 pounds. And some of that, again, may be some slight issues with that baseline specimen that we need to reevaluate. But where we saw the most positive result was on the type K shrinkage compensating or expansive cement, which tends to need the most detailed curing process. Again, our reference line there shows the largest shrinkage, and as we increased the internal curing water, we continued to see a decrease in shrinkage. So this is kind of where we start to get motivated toward what we're doing now, where we see that adding that internal curing water is helping us with our cement hydration and with our expansion. So if we look at the internal vibrating wire strain gauges, which are going to pick up the earlier age expansion than what we were able to see with some of the C157 tests, which don't start picking up until 24 hours. If we look at our reference blue line in this case, we can see a drastic change in the performance of these mixes because we're catching the increased expansion at early ages. This was really interesting as an initial result. We also had we'll say a mistake that happened that led to an additional interesting result, which I'll show here. One of the specimens that we cast with the type K expansive cement concrete, or one of the mixes actually, ended up with a much lower water cement ratio than we expected. Students didn't catch that one of the buckets was leaking, and by the time we realized that that was a problem, they had already cast the specimens, and we'd already instrumented them, so we just left them and started recording data. And we saw a drastic expansion from these specimens over the first few days. and we saw it enough that it was almost 1/4 of an inch of increase in the length of the specimen. And this was one of the ones including, I think, 7 pounds of internal curing water. So this kind of motivated our thinking for the future, we'll say. And so then if we look at the Portland cement concrete, we can see that we didn't see a lot of increase for the 5 and 7 pounds, or a lot of change for the 5 and 7 pounds of internal curing water. But as we went out to 10, we did see a reduction in that drying shrinkage over time. So the conclusions that we could draw from this kind of initial study was that we did see an increase in compressive strength as we included internal curing. Again, without any kind of external curing included. We saw the least amount of shrinkage when we had 7 pounds of internal curing water for each type of cement. And then while the large ranges of our RCIP tests made the results somewhat inconclusive, we did see some changes that indicated the potential for internal curing water reducing that permeability. And then our type K cement showed the most overall improvement in both compressive strength and length change, and then also the best results relative to permeability. Okay, so that's what we have kind of done. And so kind of where we're at now is looking at a further investigation into internal curing of types K cement concrete, a new cement that didn't exist at the time of this preliminary study that's an expansive BCSA cement, as well as a typical BCSA cement that we're looking at different water cement ratios, cement contents, and curing conditions along with the internal curing. We're also looking at a higher percentage of replacement with type K. So in that previous work, we had a 15% replacement. We're moving up to a 25% replacement, which will lead to a larger expansion and will make the impacts potentially of internal curing more obvious. So if we look at the compressive strengths of these materials without any internal curing, the expansive BCSA reaches a high strength. Typically, at least for the mixed designs that we're using in this case, whereas the type K is lower. But we see a lot of increase in that compressive strength as we do our curing, which is what's highlighted in blue there. So kind of our preliminary results with the 25% type K, we see a substantial increase in that compressive strength with the addition of either 8 pounds or 10 pounds of internal curing water per 100 pounds of cement. And then kind of where I'm going to end is the ongoing parts that I don't have results to present to you yet. But just to give you an idea of where we're heading, if we look at these graphs, these are the expansive BCSA on the left and the 25% type K on the right. These are unrestrained expansion ASTMC 157 as well as restrained expansion ASTMC 878. The blue line and the orange line in both cases are continuously water cured. And so we see expansion and then we kind of see a plateau in that expansion for the type K. We see a gradual increase over time for the expansive BCSA. But if we stop that water curing at 7 days, we start to see that shrinkage. And so this is where we are looking at the impacts of internal curing on these cements. The same thing goes in looking at creep behavior. The expansion of these cements has the potential, or offsets some of the creep behavior. This was really interesting in a pre-stressed element, but being able to maintain that expansive behavior after we're able to stop curing has a lot of potential there for these materials. So that's kind of where we're at right now, continuing to work. If you have questions about anything we have done or are working on, I would be very interested in talking to you, or if you have any questions I can answer today, I'd be happy to do that as well.